Can you guys hear me?
Yeah.
Okay, perfect. Okay, so we left off talking about molarity. Can you guys see this, the PowerPoint?
Yeah.
Yeah. Okay, so remember a mole is the molecular weight of all the molecules in a compound. So we did glucose as a practice, we did water. So now we're going to do something a little more complicated, which is sucrose. Sucrose is also table sugar, so you're pretty familiar with this. C12H22O11. So we just break it down. Carbon's molecular weight, if you look on the periodic table, is 12 Daltons. And then hydrogen's molecular weight on the periodic table is 1 Dalton. And then oxygen's molecular weight is 16 Daltons. So now we just have to multiply all these numbers together. So 12 for carbon for its molecular weight, and there's 12 carbons in sucrose. So 12 times 12 is 144 Daltons, and that's carbon's contribution. And then hydrogen is molecular weight is 1, and there's 22 hydrogens, so we have to multiply that by 22, and we'll get 22 Daltons. And then oxygen's molecular weight is 16, and we multiply that by 11 oxygens because there's 11 in it, and that gives us 176 Daltons. And if we add this all up, we get 342 Daltons. But remember, because we're doing moles, we have to convert the molecular weight of that compound to grams. So all we just do is put, instead of putting Daltons, just put grams. And so the 1 mole of sucrose weighs 342 grams. So if I ask you to bring me a mole of sucrose, you could get a bag of sugar from the grocery store, pour it on a scale until it weighed 342 grams, and then hand it to me. And that would be a mole. So a mole is actually called Avogadro's number. It's the number of molecules in a mole. So basically, you can go back and take the actual weight of a Dalton on the metric system and calculate. So the actual weight of, say, 1 hydrogen atom, because that molecular weight is 1, and then you could figure out how many Daltons would it really take to make a gram. So there's no magic trick involved, like just going, I'm just going to erase Daltons and put grams in its place. So this guy did the math. Avogadro did the math on it, and he found out that there's 6.02 times 10 to the 23rd molecules in 1 mole. So 1 mole of hydrogen is 1 gram, and that 1 gram contains 6.02 times 10 to the 23rd atoms of hydrogen. Does that make sense? Can you guys hear me?
Yeah.
All right. So it just turns out that this number is the same no matter what. Like if we're talking about water, so for water, this thing is all connected, right? So if we're going to add, if we add up the molecular weight of each of these, it would be 16 plus 2, which would be 18 grams would equal 1 mole. And because they're all connected, so this is considered one molecule, there's still the same number of molecules in any compound. So in water, there's 6.022 times 10 to the 23rd water molecules in 1 mole, and that would weigh 18 grams. Does that make sense? Because they're all connected together. Like, you know, if you're not counting individual Lego blocks, you're just counting the Lego fire truck that you built. And so it wouldn't matter if you had one Lego block or one Lego fire truck, they still count as the same. They're just one. Does that make sense? Even though
Yeah.
one's smaller than the other. So that number never changes, and that's just a number that you guys need to memorize. I don't think I asked you anything about Avogadro, but you're going to need to know this for chemistry anyway, if you ever take chemistry. All right. So the reason for all that junk, the reason that you need to know this is because when we make solutions in biology and chemistry and science, we generally use either a percent or we use molarities. This is really common. In fact, if you ever worked in a hospital or ever had an IV, you would see that it's the IV units, or the amount of salt in the IV unit is usually in moles. What is molarity? Well, molarity is defined as the moles of the solute. So what's the solute? You remember? This is an aqueous solution.
It's the mixture, right?
So a solute is the what's being dissolved, right? So in this case, if we're making salt water, the solute would be salt. Make sure you guys know these terms. The solvent is what?
What's dissolving it?
Right. And in this case, it would be
Water.
Water. And then the solution is salt plus water. Does that make sense?
Yeah.
Okay. So we have to look at this definition. It's a little funky, but this is just how it's done in science. So the moles of solute per liter of solution, right? So this is the key. It's the solution, not the solvent. So you can't just take, so we just did sucrose, right? So let's say we're going to make sugar water. And we already know that 1 mole of sucrose, and this is how you write out a mole as a shorthand. 1 mole of sucrose is 342 grams. All right. So, and we know sucrose is going to be our solute because that's what we're going to dissolve in our water. So you'll take a bag of sugar and pour it on a scale and weigh out 342 grams. And then you could put it in a container, like a big flask or something. So I'm just going to draw it. And you poured your mountain of sugar in here. 342 grams of sugar is a lot, by the way. So here's your sugar in your container. Now, the solvent we're going to use here is water. So we're going to take water and we're going to pour it in this container. And let's say this is the mark on it, just like in your measuring cup, and that's 1 liter. So you pour the water in there, but can you pour a liter of water in here? to make a molar solution?
No.
Yeah. So the reason is because if you poured a liter of water in here, it would go over the 1 liter mark. It's just like if you filled up your bathtub all the way to the top and then got in it, what would happen?
It would overflow.
It would overflow, right? So because the sugar is taking up space, just kind of like you in your bathtub, you can't put it all the way to a liter mark and then add the sugar in there. So what you have to do is you add a little water. So add less, let's say you add a half a liter. And then you want to try to dissolve this sugar with that half a liter. And then you keep adding the water in here until it reaches this 1 liter mark, right? And so that's the solution, right? The water and the sugar together have to be 1 liter. 1 liter. So to make a molar solution, 1 molar, and that's a capital M, that's the abbreviation. Make sure that you know the difference between this, which is a mole, and this, which is molar, which refers to this definition here. All right. So any questions about how to do that? Now, let's say that let's do another practice one real quick. Okay, so let's say that I'm just making this up, but let's just say that there's a horrible car accident outside wherever you are right now, and you're going to go and make a whole bunch of IV bags to save a bunch of lives. So we want to make an IV, and we need to make the IV, we have to dissolve salt. And we'll talk about why that is when we get to the movement of water across a membrane. Chapter, it's either 7 or 8. All right, so we need salt and we need water. So you run to your kitchen, you grab a thing of salt without iodine in it, and you're going to make a 1 molar. You need to make a 1 molar, remember that means molar, molarity, of solution of salt water, and you're going to make 1 liter of it. So sodium, its molecular weight is 23 grams. Remember, it's Dalton's, but we just switch it to grams to do this. And then chlorine, so sodium is 23 grams. Chlorine is 35.5 grams. So how much salt would you weigh out to get one? You need 1 mole. Remember, this is the shorthand for mole of sodium chloride salt.
Would it be the 23 grams?
So it's 23 plus. Remember, these are connected together, so we have to add them together. So it's 23 plus 35.5, which would be 58.5 grams. And you'd weigh that out, and then you'd get a container that was measured to 1 liter, and you put the salt in there. Now, do you pour a whole liter of water in there?
No.
No. So you're going to add some water in here until the salt dissolves, and then fill it all the way up to 1 liter, and that gives you a 1 molar solution of sodium chloride. You can do that for anything. So when you're making any aqueous solution, you can do that. Any questions about that?
No.
Okay. have that exact example on the next slide. Okay, so one more thing I want to say about molarity. So we just made a 1 molar solution. We made 1 liter of a 1 molar solution of salt, right? But let's say we don't need that much. Let's say we only need a half a liter. So instead of adding 58.5 grams, because if let's say this is the liter mark and this is the half liter, would I want to put 58.5 grams of salt in here to make
No.
1 molar? How much would I want to put in here?
Would you just do half of that?
Right. So all you're going to do is multiply it by whatever fraction it is. So we multiply that by 1/2, and that gives us 58.5. We can get rid of that 1 because we're doing the multiplication, divided by 2, and so that would be 29.25 grams, right? Or let's say I wanted to make a half a liter of a half molar, so 0.5 molar of sodium chloride. How would I do that?
Divided in half again?
Right. So you could multiply these together, 0.5 times 0.5, which would give you a fourth, 0.25. And then you just multiply that by the molecular weight in grams. So that's 58.5 grams. And then we could just do the math on that. And by the way, you guys can use a calculator on the test if you want. It just can't be graphing or programmable. 58 times, and we would weigh out 14.65 grams, and then add that to our half liter. Does that make sense?
Yeah.
So you can manipulate these numbers depending on the amount that you need to make and the molarity of that solution. And on the test, there'll be things like this. Like I will ask you, make me a 1/4 molar solution of sucrose, and I only need a 1/4 liter of it. And so you would just multiply a 1/4 molar by a 1/4 liter, and then multiply that by 342 because that's the molecular weight of sucrose. And you might have to calculate this. I might just give you the masses of carbon and oxygen and hydrogen, and you'd have to calculate the number of moles, the number of grams of sucrose in 1 mole. So this is the application part of the class. Like you need to apply what you learned in order to answer the questions on the quizzes in the exam. And there's practice questions on the quizzes as well. Okay. Any questions about molarity?
Nope.
Awesome. All right, so we're going to get into acids and bases. So in pure water, the concentration of hydrogen ions equals the concentration of hydroxyl ions. So here's what's going on. Remember that oxygen is super selfish. It has a really high electronegativity. And so the electrons spin around it really often, hardly ever around hydrogen. So what happens is sometimes, because oxygen is so selfish, it forgets to share with hydrogen. And so if it doesn't share, if it's not sharing electrons, what happens to this bond?
Does it weaken?
It doesn't weaken because remember, a chemical bond is either sharing or transferring of electrons, either covalent or ionic. This is covalent. So the definition of a covalent bond is sharing electrons. So if it's not sharing electrons, what happens to this covalent bond?
Okay, I found
It would break.
electrons.
I did
So
not
if it's not
ask you,
sharing
Siri.
electrons,
If it's not sharing electrons, what happens?
It would break.
Right. And then so this hydrogen, remember hydrogen is, excuse me, hydrogen's molecular weight is 1 and its mass is 1. So hydrogen is 1 proton, and to make it electrically neutral, it's 1 electron. But it left, and oxygen still has its electron. So what happens to the charge on hydrogen? If it no longer has an electron, it's just a proton. What's the charge on a proton? Again, you guys will need to be able to apply this, and we covered this in chapter 2. So remember, proton is a plus charge, electron's a minus charge. Since there's no minuses, what would be the charge on hydrogen?
1
Plus.
plus 1.
Right, plus 1. And then what would be the charge on this that's left over? Because it's like an O and H. By the way, what is that called? You guys that did the chemistry.
Carboxyl, carbonyl.
No.
Hydroxyl.
Yeah, it's a hydroxyl group. So what's the charge on this hydroxyl group? Remember, it has an extra electron because it took it away from hydrogen. It didn't share.
Is it a negative charge?
Exactly. So remember we talked about ions. So I might ask you on the test, is this an anion or a cation?
Anion.
Right. Remember, ana means up. And so it has an extra electron, so it's bigger. And then this is a cation. And this means down, and it's smaller because it has 1 fewer electron. So this is what happens in water. If you had a glass of water and you could shrink yourself down, you would see that this happens at a specific rate. It doesn't happen all the time. It's not very common. It occurs at the rate of 1.0 times 10 to the minus 14th moles. And yes, water can have a mole, because if you took water and dissolved it in itself, then 18 grams of water would equal 1 mole. So it's kind of weird because it's not really a solution. It's the solvent and the solute are the same. So the solution's the same. It's not really a solution, but anyway, just for all intents and purposes, this is the occurrence of that. And so what this means is that the number of hydroxyls formed plus the number of hydrogen formed equals this value. Because it's water, right? Every time we make one of these, every time we make a hydroxyl, we have to make one of these hydrogen ions. Does that make sense? Because it's water. So if this comes off, you get one of these and one of these. It's like, shoot, what can I make an analogy of? If you broke a pencil in half, you would make 2 halves of a pencil that would be equal. There'd be 2 of them because they came from 1 pencil. Does that make sense? Yes, no, maybe so. Let's do it this way. If you built a water molecule, so let's say that you took an orange and 2 lemons and stuck them on sticks, right? And then you decided you were going to pull one of the lemons off. So every time you did that, you're going to have two separate things, one lemon and one orange stuck to a lemon. Does that make sense?
Yes.
All right. So every time we make hydroxyl, we make hydrogen, which means they have to add together. So the number of these plus the number of these has to equal 10.0, 1.0 times 10 to the minus 14th. So that means that we can half this value because there's two of them. We add them together, they have to equal this. So that means that the number of hydroxyls in pure water is 1.0 times 10 to the minus 7th. And sorry, we multiply them. Sorry, yeah. Hydrogen is 1.0 times 10 to the minus 7th. All right, so in a neutral solution, the number of hydrogen ions always equals the number of hydroxyls because it's pure water. Does that make sense to everyone?
Yes.
Okay, awesome. So because of this value in moles in water has to be 10 to the minus 7th for the hydroxyl and the hydrogens, then we use this value to calculate pH, because pH literally means the power of hydrogen. All right. So in a neutral solution, what we're concerned about is what the amount of hydrogens, the H pluses, are in the solution. This affects the pH. And all you have to do is take this exponent that's negative and convert it into a positive number, and that's the pH value. So what's the pH of pure water?
7.
Yeah. And it's always 7, but it has to be pure water. If the hydrogens increase, they're bigger, then it's acidic, and if the hydrogens decrease, then it's basic. So I'm just going to explain this a little further. Okay, so let's say that we were adding in hydrogens. So we just have a way to do this. So we added in hydrogens into water. Then when this occurred, and this went off on its own, this would pair with the other hydrogens and leave this one with no one to pair with. Does that make sense? So we're messing with the ratio of these. We're going to increase these because they have nowhere to pair. And so let's say that we added them in, and remember this is a, so I'm not going to write in the 1.0 because it's just what 1 times anything is itself. So I'm not going to write that in. But let's just say that the pure water solution is 10 to the minus 7th hydrogens, right? Because that's what we're concerned about for pH, and that makes it a 7. But I'm adding in hydrogen. So what happens to this number? Does it get bigger or smaller?
Well, more hydrogen. Does it get smaller?
If I add stuff, if I give you extra money, does your wallet get smaller or bigger?
It gets bigger.
Okay, so then this number would get bigger. Well, the amount, but because it's a negative exponent, right? Like 10 to the negative 7th is 1, 2, 3, 4, 5, 6, like that. If I made this 10 to the negative 8th, it would be that. So, right, so this number is actually smaller. 10 to the minus 7 is small or bigger than 10 to the minus 8. Does that make sense? So as this number gets bigger, the actual number of molecules gets smaller. So if I'm adding hydrogens in and it was 7, to the negative 7, and let's say I pour a bunch of hydrogens in there, that might make it go to 10 to the negative 5th. So what does that do to the pH then? What would be the pH value?
It raises it.
So what number? What's the actual value of the pH here? 1.0 times 10 to the negative 5th hydrogens.
Oh, it lowers it. So
So
maybe-
what's the number? What's the pH? If it's 10 to the negative 5th, remember we take this number, we make it positive.
So it's 5 and it would be basic.
5, and remember these are bigger. This is more. Even though this number got smaller, right? Negative 5 is right, and as I keep going to 1, that number is bigger. This number here is bigger than this number. 10 to the negative 5th is a bigger value than 10 to the negative 7th. Do you guys get that?
yes.
So there's more hydrogens, and if there's more H pluses than OH minuses, then it's acidic. So that's why the pH scale is really weird. And I didn't make this up, so don't blame me, but it is confusing. But we can do some examples here. Okay. So if I ask you on the test, you would have to have a way to measure this. So if I ask you on the test, if you to take this, so you have a way, come on. You have a way of measuring the H pluses in a solution, and you figure out that those H pluses is 1.0 times 10 to the negative 3rd. I'm going to ask you on the test, what's the pH? What is it?
3.
Yeah. And I might say, okay, you don't have a way to measure the H pluses. You can only measure the OH negatives. And that's turns out to be 1.0 times 10 to the negative 8th. What's the pH?
It's still equal 8.
No, because remember pH is power of hydrogen. So what you have to figure out is, remember together they have to equal negative 14.
Oh yeah.
What do we have to add to negative 8 to get to negative 14? What do we have to add to 8 to get to 14?
So 14 minus 8 is 6.
Right, you'd have to subtract 6 from negative 8 to get negative 14, which is the magic number. Remember, they always have to add together to be 10,
14.
multiply together to be 10 to the negative 14th. So the answer to this is the pH is 6. Right, because I didn't give you the hydrogens, you have to figure it out on your own from the hydroxyl value. So let's try it this way. What if I said we measured the H pluses and it turns out to be 0.00007 moles? What's the pH? And you would need to convert this to scientific notation. And you're going to do this in the metric lab whenever you guys turn this in. But so you move the decimal 1, 2, 3, 4, 5, 6 places. So that's 1.0 times 10 to the negative 6. Because that's how I'm moving the decimal. And so what's the pH of this solution?
Six.
Yeah, because I give you the hydrogens, right? So let's try one more. Okay, so we have this is the molarity of the OH value here. So what is the pH? By the way, I drew a 7 on that last one, but I wouldn't do that. It would be a 1. So we have to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to get it to be 1.0 times 10 to the negative. That would be 1, 2, 3, 10 places. So that equals 1.0 times 10 to the negative 10th. So what's the pH of this solution?
4.
Exactly, because negative 10 minus 4 equals negative 14, which is what we have to figure out. So the pH here is 4. Since I didn't give you the hydrogens, I gave you the hydroxyls. So everybody get that? And when you do the quiz, you'll see that there's a lot of practice problems. Any questions about pH and how to calculate it? So again, it's just going to take some time for you to practice this, and the more you practice, the better you'll get at it. But that it'll definitely be on the test.
What do you want to watch, Maria? No, watch something else. What do you want to watch?
Okay, so if let's say we pour the hydrochloric acid
You want to watch Leap?
into water, you can do that in your swimming pool. Sometimes they call it muriatic acid. It's basically the same
Why are
thing.
you not going to eat all your chippies?
So we pour this in. And what do you think is going to happen to this water? Is it going to get acidic or basic?
Acidic.
Right. And why is that? Well, hydrogen's charge is a plus, right? And chlorine's charge is a minus. And you can do the electron configurations and figure that out. But when you pour this in water, remember water can dissolve anything that has a charge. So water will surround the chlorine on the hydrogen side, and water will surround the hydrogen on the oxygen side. And we talked about that in chapter 3 or 2. Actually, we talked about it this chapter. Let me just back up just to remind you guys. So right here, we talked about like how oxygen surrounds on the positive side and hydrogen surrounds on the negative molecule. So that's what I'm talking about. And so because we're doing this, we're adding H pluses and we're also adding Cl minuses. Now, what's the definition of an acid? Is anything that increases the H plus concentration in a solution. And so by pouring hydrochloric acid into water, we're increasing H pluses. So we get the number of hydrogen ions in the solution increases. That makes it more acidic. Does that make sense?
Yeah.
Okay, cool. We can also reduce the number of H pluses. So if we poured ammonia, which is NH3, into water, remember water dissociates to a specific amount of OH and H pluses. What happens is when ammonia gets around H plus, it can take on another hydrogen, and so that makes it form NH4. So if it's pulling out the hydrogens out of the solution, then what, by definition, it's reducing the H pluses. And so if we reduce the H pluses directly, then what do you call it? You're called a base.
Basic. Okay.
So remember, acid adds H pluses and bases remove H pluses, because pH is all about the hydrogen ions. Nothing else matters. If you can't change this, then you can't make something acidic or basic, right? So let's say that you had upset stomach, like you have acid indigestion. How could you fix that?
Take away acid.
Yeah, okay, so could you drink water? Would that help?
No, you would take a antacid.
Right, water wouldn't help because water can't increase H pluses. By nature, it's already, every time you make an OH, you make an H plus, and then they form and they're constant. So water wouldn't do that. Let me just address this real quick, and then we'll move on to how antacids work. So anyway, you could also add sodium hydroxide. Remember, sodium's plus charged, OH is minus charged. We talked about that in the previous slide. And so if you add OHs into a solution, they want to make water. And so how do we make water with the OH? You have to add a hydrogen, right? Because it's H2O. So by pouring sodium hydroxide into a solution, it is removing the H pluses to make water. Does that make sense? So when it takes away hydrogens, what do we call that? Removes a hydrogen. It's a base. All right, so that's an indirect method to make a base. All right, everybody understand the pH scale?
Yeah.
Yes.
So, if I said, okay, here's a can of beer, its pH is 3. What can you tell me about it?
It's more acidic.
The number of hydrogen ions is 1.0 times 10 to the negative third, right? Or you could also tell me the number of hydroxide ions is, do you know?
11.
Yep, that's right. So that's how the pH scale works. It has more H pluses than OH minuses. Even though this number is smaller, it's actually bigger. And you can do anything. So, I mean, this is just examples of biological stuff. Urine is about pH of 6. And I'll tell you guys, I think I may have talked about this story before when we talked about how the shape and why molecule shapes are important. But I'm not sure who started this, Gwyneth Paltrow or somebody, doing this alkaline diet. Alkaline means alkalinity means it's a base, right? So on this alkaline diet, it's supposed to cure cancer and do all kinds of stuff. And so they eat only foods and drink only alkaline water, and because it's more basic, and then they claim that changes your pH, right? Which is complete bullshit. It doesn't work that way. So if you drink alkaline water, what happens is that your kidney's job is to regulate the pH of your blood. pH of your blood has to be between 7.2 and 7.6. If it falls outside of this pH range, your molecules will change their shape. Then they, like hemoglobin, for example, if it changed its shape, what would happen?
Bad stuff.
You wouldn't be able to carry oxygen anymore. So hold your breath and see what happened if you change your pH of your blood. You'd die. So the people that claim that this alkaline water kills cancer or changes your blood pH are full of it. Now, I'm not going to say that alkaline water isn't helpful, because acidic water can wreck the enamel of your teeth. So that if you're doing it for your teeth, well, okay, that's great. But if you're doing it to try to kill cancer, there's no cancer in your teeth. They're enamel. So this wouldn't work because your blood pH doesn't change. Your kidney's job is to make sure that your blood stays between 7.2 and 7.6. But you could drink a whole ton of alkaline water, and what would happen? So the alkalinity has to go somewhere. Your kidneys are responsible for filtering the extra base that you're ingesting out of your body. So where's that going to go?
Into your kidneys,
And what are your kidneys empty into?
your bladder.
And then that empties into your pee, right? So these celebrities, they test their pee, and they go, oh, well, my pee is also basic. That must mean that it's working. My internet connection is unstable. Whatever. Did you guys catch that?
Yeah.
You're fine.
Okay. So it does. This alkaline diet will change the pH of your urine, but it doesn't change the pH of your blood. And the way that this came about is that in a lab, someone added alkaline water to cancer cells. And guess what happened to the cancer cells when they added the base to lower the pH? What would happen to you? What would happen to your cells if we lower the pH beyond this range?
It died?
Yeah, the cancer cells died, and they go, oh, well, adding alkaline water to the cancer cells killed them. So if you drink alkaline water, it'll kill the cancer cells too. But the problem with this is if I added alkaline water to regular cells, what would happen to them?
Also die?
Right. And so nobody tells you this. They just focus on this. And it's that fallacy of saying, okay, well, the increase in the consumption of ice cream goes up in Phoenix in the summer, and so did drowning. So ice cream must cause drownings. So anyway, your pH can't change, and it doesn't matter what you eat or drink. Your kidneys, as long as they're functioning, are going to maintain this blood pH. All right. And you also have what we call buffers in your body. So is this acidic or basic on a 2?
Acidic.
Good. Milk of magnesia, is that acidic or basic?
Basic.
Good. And what about pure water?
Neutral.
Neutral.
Perfect. You guys got it. Sweet. Okay. So remember, the pH of a neutral solution is 7. Acidic solutions have values less than 7. Basic solutions have values of greater than 7. Most biological fluids have a pH between 6 and 8. Although the pH of your stomach can reach 2 and it's acidic. And so let's just talk about this for a second. How does your stomach, this is my stick figure person. So your stomach, how does that get a pH of 2? How would you do that? You just drink hydrochloric acid all day?
From your stomach acids.
Right, but how does your body make stomach acids? How do we make acids
From your
in the
liver,
anyway? Like
from your
we just
liver.
talked about that.
your liver and your gallbladder, your bile.
Well, don't get specific. How do I make an acid? How do I make the pH go down in something? What do I have to do?
Add more hydronium ions.
Yeah, hydrogen ions. Right. I have to increase hydrogen ions. So the way this works is there's cells that line your stomach. They're called parietal cells. You don't need to know that, but those cells' job is to take hydrogen ions from your blood and pump them into your stomach. So they are what we call hydrogen pumps, and we're going to talk about this when we get to chapter 8. So these cells, these parietal cells, are constantly pumping H pluses into your blood, and there's a pump right here, a pump receptor that does that. You guys ever heard of Nexium? The purple pill that
Yes.
you take for
Yeah.
acid reflux? Nexium is kind of a cool medication. What it does is it binds to this pump and blocks it. So what happens is you can't put H pluses in your stomach anymore. And what happens to the pH if there's less H pluses?
It becomes less acidic.
It's less acidic. And so that's how that drug works. It's a proton. This is a proton, right? Because hydrogen normally is one proton and 1 electron. But if we take away the electron, we make H plus, which is what's left.
The proton.
Just a proton. So we call this a proton. Hydrogen ion and proton mean the exact same thing. So if you look up Nexium, and you guys can do that if you want, it's a proton pump inhibitor. And that's how it works. So you could take Nexium and reduce the acidity of your stomach, but you also know that you could take Tums or something. And what Tums does is it acts as what we call a buffer. And buffers take strong acids and make them into weak acids, and they're what we call conjugate salts. And I'll show you that in a second. The other thing that you should remember also is one pH unit is a tenfold difference, right? The difference between 10 cents and 1 cent is, this would be 10 to the negative second, and this would be 10 to the negative first. So the difference between those two is actually tenfold, right? You need 10 pennies to get a dime, and you need 10 dimes to get a dollar. So every one of these units, because it's to the 10 to the power of something, is a tenfold difference. So I might ask you on the test, the pH of your blood is 7 and the pH of your stomach is 2. How many more hydrogen ions are in your stomach than in your blood?
A lot more hydrogen ions.
Well, I would need a specific number. There would be a specific number on the test. So this is 10 to the negative 7th, right? And this is 10 to the negative 2nd. What's the difference between those two?
10 to negative fifth more.
Well, when we have the two negatives, it becomes a positive. So 10 to the negative 5th, we'd actually make that a positive. So it would be 1 with 5 zeros after it. So there's actually 100,000 more H pluses in your stomach than in your blood, because each one of those is a 10-fold increase. Make sense?
Yes.
All right. So that's a big number, even though it's the difference is small. All right. So this is how Tums works. So it's not a proton pump inhibitor. It directly interacts with the acid in your stomach. So it's calcium carbonate. This is sodium, but you could easily replace this with calcium, and it's the same thing. So sodium bicarbonate is actually baking soda, and baking soda can also reduce your stomach acid. If you have that around, you can take that, and it acts just like Tums, which is calcium carbonate. Anyway, so if you have a strong acid, like the acid in your stomach, that's a very strong acid. Remember, we said the pH of that is about 2. And we add a buffer like this sodium bicarbonate or calcium carbonate is a buffer, then it makes a weak acid. This is carbonic acid. Its pH is around 4. So that's about, I mean, it's a small change because it's only 2, but how many is it really? It's 10 to the 2nd, which is 100-fold reduction in hydrogen ions. And then because the hydrogen ions are going into there's 2 of them getting pulled out. Does that make sense? Because it's H2 and adding in here, and then this makes salt. So when you take Tums, it's actually buffering or removing the H pluses and adding it to carbonic acid, or producing carbonic acid. All right, so and that's how this works. But the most important thing in here of this slide is that substances that minimize sudden changes in pH of a solution are called buffers. And anytime we're working with a biological system, we have to make sure that we are using buffers. So if we're working with enzymes in the lab, we have to make sure that the pH stays the same, because what happens if the pH changes? What happens to the shape of enzymes or proteins, by the way? So what happens to the shape of the enzymes when we change the pH?
They would fall apart.
Right. Well, it would definitely change its shape. It's just like temperature. So if we heat something up or we cool it down, it changes its shape. Same thing with pH. So the two worst enemies of living systems is temperature, which is the average kinetic energy. So it's not really the same as heat, but let's use temperature, and pH, right? These 2 things will change the shape of your molecules, like hemoglobin, for example. And if hemoglobin doesn't have the right shape, it can't bind oxygen. And if you can't bind oxygen, then what happens? You die. So if I change your pH, you would die. If I put you in the oven, you would die. If you had a really high fever, you know, and these are delicate systems. I mean, let's just say that you had 110, let's say you had 108-degree fever. What would happen to you?
Your molecules would
Cook.
change.
You would die, right? Normal body temperature is 98.6. So what's the difference between these two?
About a 10-degree difference.
Yeah. So if your body temperature went up 10 degrees, you would be dead. If it went down 10 degrees, you'd also be dead. It would take longer to kill you if you cooled you off because molecules move slower when you were cooler, but you'd still eventually die if your body temperature went down to 88.6. Your molecules would change their shape and you would die. So same thing with pH, right? Remember the pH is 7.2 to 7.6. So these are very small windows that life can exist at. All right, so we're done with chapter 3. Do you guys have any questions about that?
Nope.
So I'm just going to download chapter 4 real quick. All right, now I just got to switch to the screen and share. Okay, can you guys see chapter 4?
Yeah.
Okay, perfect. So chapter 4 is basically organic chemistry. So I know that that's a scary word. That was my least favorite subject, but you can't be a biologist or know anything about life unless you suck it up and learn organic chemistry. So it's just kind of to me, it's a necessary evil. Not my favorite subject, but you guys decide you're in biology for a reason, so you're gonna have to learn it. Carbon is super important, and the reason it is because its valence is 4. And we talked about that. So that means that it can make 4 bonds. Remember, hydrogen valence is 1. So the simplest hydrocarbon that we can make would be carbon with 4 hydrogens attached to it. Any other molecule wouldn't be able to make as complicated of a structure, right? Oxygen can only make 2 bonds. So nitrogen can only make 3 bonds. Hydrogen can only make 1 bond. So of all these, carbon is the only one that can make 4 bonds. And the more bonds you can make, the more complex structures you can make. And if you don't believe me, you can go get a stick and add oranges to it or whatever, and you'll see that if each one of your oranges can make 4 connections, you can make a lot more complicated things than if they could only make 2 or 1. And so that's why carbon is really important to living systems, because we can make super complicated molecules out of carbons. All right, so we've talked about carbon. Carbon, you know, is atomic number is 6, and if you forgot that, you don't have to memorize it. Eventually, you will, like I have. But you can look at the periodic table, and because its number is 6, we know it has 6 protons, and its mass is 12. So it has 6 electrons, and it also has 6 neutrons. because this adds 6 Daltons to it, and this adds 6 Daltons. And remember, this is 0, so that would give us a mass of 12. And then we know that if we're drawing carbon out, the first shell has 2 electrons in it, and then the second shell would have to have 4. And remember, they're not paired. 1, 2, 3, 4. And you guys need to be able to do this for the test, so we need to practice this. And so it can form 1, 2, 3, 4 bonds by sharing these 4 unpaired electrons. So that's why its valence is 4. It has 4 unpaired electrons in the outer shell, and that makes it allowed to form 4 covalent bonds. So we say that carbon is tetravalent. What do computers run on? You guys know? They're all on silicon. And if you look at the periodic table, you'll also see that silicon has a valence of 4. Coincidence? It's not. Because you can make complex things out of silicon. Okay, so you're just going to have to memorize this. The simplest hydrocarbon we can make, because carbon can make 4 bonds and hydrogen can only make 1, so we can't add anything over here. That would be impossible. This is the simplest hydrocarbon, which is CH4, and that its common name is methane. This is what you smell when you're around a cow farm. So it's the gas in human emissions. And then, so we could also do 2 carbons, and if we filled them with hydrogen, carbon's only allowed to have 4 bonds max. So this is fully full of hydrogens, and so this would be, if it has as many hydrogens as it can take, we call that saturated. Kind of like saturated fat versus not saturated. So anyway, this would be C2H6, and this is ethane. And then we could keep going. We have 3 carbons, and then we just fill it with as many hydrogens as we can. And this would be C3H3, 4, 5, 6, 7, 8. This is propane. You guys are probably familiar with that if you use a gas grill. And then I'm going to jump over here and we'll do the last one, which is C4. And you're just going to have to memorize the names. Drawing this out is pretty simple, because if you just add 1, 2, 3, 4 carbons, and then you know that carbon makes 4 bonds, then you can easily add in all of the hydrogens. So this would be C4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10, and this is butane. And if you ever used a cigarette lighter, you know what that is. So all these are the basic hydrocarbons that you need to know. And have you guys ever gone to the gas pump and it tells you what's the difference between premium gasoline and the other gas, like the cheaper gasoline? Do you guys know? So it has numbers on it. It's like 87 and 91. Do you guys know what those numbers are?
The higher number is the higher octane.
Octane, yes, that's what I'm getting at. So what do you think octane looks like?
Are there 8?
Exactly. So octane, just like octopus has 8 legs, is, you know, come on. 1, 2, 3, 4, 5, 6, 7, 8, and then we just fill it with as many hydrogens as there are can go on here. And I'm not going to do the whole thing, but this molecule is octane. So notice that they all end in A and E. And so like methane, and so you need to know methane and ethane and propane and butane. That's all. Those 4 are the ones you need to know for this class. And there's more like octane and stuff like that, but you don't really need to know that. I'm just showing you that these things are familiar to you, that you're around them every day. So carbon can also form double bonds, right? And so if we have, we're going to take ethane, which is this molecule here, and we're going to add a double bond to it. So instead of 1 bond, we have 2, and that's going to change this molecule because we have 2 bonds. That means that there's only 3 left, or 2 left, for, because we have 2 here. So there's only 2 left that carbon can make instead of 3. And so that makes that molecule have a different shape. And in biology, shape is the most important thing. And if you have a different shape, you're going to react differently. You're going to behave differently. You'll have different melting temperatures and boiling temperatures and different chemical properties, just like we talked about with, sodium's an explosive metal and chlorine's a deadly gas. And we put them together, it changes their shape, and now it's salt, which is safe. So when we have a double bond like this, it's a different shape, and you guys can just look at it and see it's a different shape. And that means that it's different. So this is actually called ethene. We change the A to an E to symbolize that it has a double bond in it. Any questions about that? So just make you some flashcards, and then you should be able to sight recognize and name these molecules for the test. All right, we talked about the valence of the big 4 for life already. All right, so when we're drawing out these structures, we call that the carbon skeleton, right? And carbon skeletons can vary in length, shape, number and location of the double bonds, and other things that are bonded to it. So I'm just going to give you an example of the length right here. So we can take the molecule butane, and so we know that that's C4, and then we fill it up with hydrogens, and I'll end this as soon as I get done with this structure. And that's H10. You guys can count them up and double check me, but it's C4H10. But I could also draw it like this. And then I fill it up. One, two, three, 4 for that carbon. And then this one. Do these have a different shape?
Yeah.
Then they're different molecules. But what's funny is they have the same chemical formula. You guys see that?
Yeah.
So this is where it gets kind of tricky in organic chemistry, because we can change the shape without changing the chemical formula. And we have to figure out a way to distinguish these 2 from one another, because we don't want butane. This is called isobutane. you guys are familiar with this because you're familiar with like isopropyl alcohol, and that iso tells you that it has this shape rather than this shape. So we have to figure out how to name this and differentiate these different shapes and locations of bonds and all that other stuff. So I'm just going to leave you with this slide, and I'll go over this slide. But we already talked about what ethane is. Remember, I told you I had to memorize that, and propane, and butane, and methane. But we just drew out isobutane, and these have a different shape, and they're different chemically. They react differently. They have different properties. And then we can add in double bonds at different places, and that also changes the structure. And so we have to number the carbons which tells us the location of the double bond. So this is called 1-butene because the double bond is on the first carbon. This is called 2-butene because the double bond is on the second carbon. Do you guys see that?
Yeah.
And then we can make ring structures. So that's funky. We can put double bonds in ring structures, and that's funky. So we can do all kinds of things with carbon and make all kinds of crazy shapes and do all kinds of crazy double bond additions, which allows carbon to make all kinds of different chemicals with different properties. And it really allows life. That's how we make different proteins, by adding different molecules and functional groups and stuff to them, which you kind of got a feel for when you did the chemistry lab. But anyway, I'm going to end the lecture here. Do you guys have any questions?
No.
Nope, seems pretty straightforward.
All right. I mean, I know that it can get complicated and there's lots of things to remember here, but just, try to systematically tackle it. It's just like trying to learn somebody's name or learning somebody's phone number. You just got to do repetitive or mnemonic tricks so that you can remember, what methane and ethane and propane and butane are. So, however you need to do to learn this stuff, make sure that you do it, and don't wait till the last minute because you won't be able to make those neural connections you need to make. And otherwise you won't remember it. All right. So you guys have a good weekend. I'm going to jump over to office hours. If you have any questions, you can hit me up there.
Thank you, Professor.
You're welcome.
Thank you.
I'll see you guys later.